Things we're doing today, we're going to teach you recursion, but the issue is all the problems that we're going to look at today, there is a way for you to do them with a typical for loop, as in you don't necessarily need recursion for them. That won't be the case for tomorrow. Tomorrow, we're going to introduce a whole new set of problems that actually require recursion, as in you can't do them with a for loop. So as we cover recursion today, and as you work on the workshop, just kind of keep in mind that when you look at the problems today, you're absolutely right if you think, oh, I can just do this with a normal for loop. You can, but for the purposes of this class, we really want you to get some practice using recursion, and then tomorrow you'll kind of see that translated into a scenario in which traditional loops just don't work. So today we're talking about recursion. Which means we need to talk about something called a call stack, and then we'll go through a few examples of recursions, and then talk through some very common use cases for applying recursion. Usually, it's iterating through something, whether it be an array or an object or a string. Okay, so the most kind of plain vanilla definition for recursion is that it's defined as something as a phenomenon in which a function calls itself. Um, it's an alternative to iteration, which is using a loop. Iteration essentially means going sequential, as in we designate a starting point and we designate the endpoint, and we just kind of go through it. Recursion is more useful than traditional iteration for a few reasons. It really breaks the problem down to the most basic principle, as in what are you trying to do over and over and over again, and that actually restriction makes people, or at least hopefully makes you think a little bit more critically about when you write a function where you're actually trying to achieve. It's easier to read because usually most recursive functions do only one thing, um, and uh, and 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 the only downside to recursion, other than the fact that unless it's poorly written, is that recursion is very memory intensive, whereas a traditional for loop can be more memory safe, I guess. And we'll see why that is in a little bit when we talk about the call stack. And it's very useful when we're talking about more advanced computer science topics like AI and machine learning. Okay, so the call stack. JavaScript is a single-threaded language, which means that we can only do one thing at a time. Single thread, you can think of it as you're at a supermarket and there's only one checkout line open, right? It doesn't matter how you do whatever you want to do. There needs to be an order in which something goes through, and everything has to go along the same exact process. In JavaScript, one of the things that we've been pretty much taking for granted so far is that if I have 10 lines of code if I have 10 lines of code going down the page sequentially from lines 1 through 10, we've always been assuming that line 1 will run, and then line 2 will only start running once line 1 has finished. Similarly, line 3 will only start running once line 2 has finished, and so on and so forth. We've taken that linear fashion for granted, if you will. And the reason why we're able to do that is because JavaScript is a single-threaded language, which means we can only do one thing at a time, and the next thing cannot start until the previous thing has finished. The call stack then essentially is a way for JavaScript to keep track of what it's doing and knowing when do we need to finish the thing at hand versus when we're able to move on to the next topic. The one common way that people have described the call stack is if you think about a stack of plates at a buffet line. If I have a stack of plates at a buffet line, usually if I want to grab a plate, I wouldn't grab it from the bottom of the stack, right? Because that requires really heavy lifting for me to move all the other plates. Instead, I just grab the plate at the very top. Similarly, if I want to put a new plate back on the buffet plate stack, if for some reason maybe I didn't mean to take a plate, I wouldn't put it on the bottom because once again, it's really hard to lift all the plates and insert the plate at the bottom. I would just put the plate at the very top. The call stack in JavaScript works very similarly, right? Think of the call stack essentially as a glorified to-do list, except there's a very set order in which we add and remove things to this to-do list. JavaScript will always work on whatever is currently at the top of the call stack, i.e. what is the thing that was most recently placed on top of the call stack. And so let's take a look at an example of that. Here on line 5, we have a function called first, and all it does is the console logs out I am first. We have a function called second, which console logs out I am second. Now, when I execute line 13, if I look at my call stack on the bottom right-hand corner here, the first thing I do is I execute the function first. And I have to console log out I am first, because when I start running line 13, the first function gets added onto the call stack, and the call stack says I cannot move on until I finish resolving this function. So then the first function runs, it prints out I am first, and then the first function is finished. When a function is finished, it gets taken off the call stack. Okay, and once a function is taken off the call stack says, okay, great, where did I leave off? Well, I left off on line 13 where I finished, and now I can start at line 14. So I execute the second function, and I print out I am second, at which point I'm done with the second function, and I take it off my call stack. Okay, if I take a look at the way the call stack would apply then for something else that we've seen a lot of so far, which is a for loop, if I do a countdown of 5, if I do a countdown of 5, here I just start at I equals num, and I do I minus minus, so I decrement I by 1 every time, and as long as I is greater than or equal to 1, I console log out num. Here, if I just run it, it will print out 5, 4, 3, 2, 1, and this is all part of one go. I.e., this is something that's all on the call stack, and as I run this countdown function, this entire function has to finish before I move on to the next thing. Okay. Sorry, that was a duplicate slide. Okay, so here, if I have another function called first, and it console logs out I am first, but then on line 3, it invokes this function called second, and then on line 4, it console logs out first is finished, and then on line 7, we have another function called second. Well, now on line 11, when I actually invoke first, how would the call stack look? Well, the first thing we would do is we would be, once again, right, lines 1 through 5 just defines a function. We've created a function, we haven't run it yet, so it doesn't go on our call stack. Line 7 through 9, we've created another function. We haven't run it yet, so it doesn't go on our call stack. On line 11 is the first instance in which we actually start running the first function. Okay, so the first function goes on our call stack, and we start running it. Well, great. If I start running the first function, what do I do? The first thing is on line 2 is I console log out I am first. So far, so good. Now, when I get to line 3, it looks like I actually need to invoke the second function. Now, here's where the call stack starts stacking up, right? Because here, realize that in order for me to finish running the first function, I need to invoke the second function, okay? And this is a very, very critical point. I cannot finish running the first function without running the second function. Why? Because line 3 says the second function has to run before I can run line 4, and then before I can finish the first function, okay? And so now, because the second function gets added to the top of my call stack, now JavaScript says, okay, let's pause on running the first function, if you will. We need to run this second function first. Okay, sorry, we named the functions very poorly, so when I verbally explain it, it's a little bit tricky. But hopefully everyone gets what I mean, okay? So because I need to run the second function as part of the first function, well, let's now resolve the second function. When I go to the second function on line 7, on line 8, I console log out I am second. At that point, I am done with the second function, so I take it off my call stack. And then when I take out my call stack, the call stack goes and says, okay, great, what was next on my to-do list? All right, it's wherever I left off on the first function. Well, on line 3, I've already finished invoking the second function, so on line 4 is where I left off, and there's where I pick it up, and I console log out first is finished, and then at that point, I take the, this is hard. Okay, so at that point, I console log out first is finished, and then at that point, I take the first function off my call stack, and I'm done with this page. Everyone good so far about how the call stack kind of works? Well, the whole premise here is that if I look at the function first on lines 1 through 5 there, in order to run function first, I need to finish running function second in the middle of it. Yeah, so here, let's go through the top again. Oh, okay, so here, if I run on line 11, I go to first function. The first line is line 2, so it console logs out I am first. Then it runs the second function, and so therefore the second gets added to my call stack. And when I invoke the second function, it console logs out I am second. At that point, I'm done running the second function, so I take it off my call stack, and then I pick up on the first function where I left off. Yeah. An analogy to make would be like, let's say I'm trying to bake a cake, right? And I have no eggs. I need 2 eggs. Well, in the middle of my cake baking process, if I have no eggs, I need to go to the store and get eggs, right? I can't keep baking the cake and then get eggs later, right? Like it's a sequential process. And so here, if I think of the first function as the cake baking process, the second function is going to the store to buy eggs, right? I can leave off wherever it is until I need eggs, but then I have to go get eggs and then come back and only then kind of pick up where I left off in my cake baking process. Yep, cool. Does this make sense to other folks too? Or any other questions from anyone else? Okay, I'm going to take that silence as everyone's good. Okay, so if you think of it earlier, we saw our old countdown function, right? Which is count down numbers from 5 through 1. Well, here, if I just want to count down from 5 through 1, I could actually do something that's kind of really repetitive, but also it works, right? Here's a countdown function. If I just count down 5 through 1, I can just do 5, 4, 3, 2, 1, and every time it works. And here, by doing it this way, I've actually kind of discovered a pattern, if you will, right? I'm calling the same function every time. The only difference is each time when I call it, I feed it a different number. And that number is less than whatever I fed it in last time. And so is there a way for us to write this in a way that's a little bit more, maybe a little bit more self-containing? And so one way for us to do this and will be to do something, and so kind of here's where we say a recursive function is a function that calls itself. Here on line 7, all I'm doing is I'm actually starting a function, is creating a function called countdown that takes in a number. And then on line 8, it prints out a number. And on line 9, it calls itself again, right? It calls the countdown function again, but except this time it inputs a number that's 1 less than what it was before. So when I call countdown 5, the first thing it does is, well, it adds countdown 5. Oh, sorry, ignore the console log. It adds countdown 5 to my call stack. Okay, well, what happens then? The first thing I do is I go line 8, and it console logs out 5. Great. The next thing I need to do is invoke countdown of 5 minus 1, which is countdown 4. And this is super critical, right? Why? Because notice that countdown 5 cannot finish until I finish invoking countdown 4. Okay, let's go back to the cake and egg buying process, right? I cannot say I'm now done with countdown 5. Why? Because countdown 5 requires me to finish running countdown 4. Okay, so now let's actually solve countdown 4. Well, when I do that, I print out 4, and then countdown 4 it requires me to run countdown of 4 minus 1, which is 3. So I need to finish that. So I can finish countdown 4, which then means I can finish countdown 5. So I print out 3, I do it for countdown 2, I do it for countdown 1, and hopefully everyone sees the pattern, right? Our countdown function is going to infinitely loop, as in it's going to keep running itself over and over and over again. It works as expected, except we didn't really tell it when to stop, so it would just kind of go towards negative infinity. In most cases, a computer that's at a certain point would just tell you, hey, your function's probably broken. It looks like you've done something, probably way more times than you intended to. And so the question now is, okay, using a function to call itself actually works for us to get to our answer. The only thing it doesn't do, or where it's kind of broken right now, is that it doesn't allow us to actually stop at the right place. And so now we need to figure out, okay, if we know how to make the function go, how do we know when to make the function stop? And so in recursive functions, the stop condition is called the base case, as in at what point does a function stop calling itself, okay? And here the answer is, well, if the number is less than 1, i.e. when we hit 0 for the first time, we just console log out, done. Otherwise, we do exactly what we were doing before. We print out the number, and then we call ourselves with the same input, but minus 1, okay? And so now when I do countdown 3, I have my countdown 3 as my original function I need to finish. Great. When I go into call countdown 3, num equals 3, and the first thing I do is I check on line 3. Is num less than 1? Well, num is 3, so it's not less than 1, so then we go to our else clause. On the else clause on line 8, we console log out 3, and then on line 9, we need to invoke countdown of 3 minus 1, which is 2. Okay. Once again, so critical, right? We are not done with countdown 3 yet. because countdown 3 can only be finished once we finish running countdown 2. So in order to run countdown 2, we do the same thing. Num is equal to 2. Is num less than 1? No, it's not. So then we go to our else clause and we console log out 2, which then requires us to do countdown 1. Same thing, we do countdown 1. Is 1 less than 1? No, it's not. So we go to our else clause. On line 8, we console log out num. And then on line 9, we do countdown of 1 minus 1, which is 0. And then now we go to our countdown and num is 0. We go to our if clause. Is 0 less than 1? And the answer is yes, it is. So then we go to console log out done. At that point, we triggered our if clause. So we skip our else clause. And at that point, we're actually done with the countdown 0 function. And because we're done with that function, we take it off of our call stack. Okay, great. When we take our call stack, the call stack says, what was next on my to-do list again before I got kind of sidetracked with countdown 0? Well, it was countdown 1. And where did I leave off was countdown 1? Well, I left off on line 9. So now that line 9 is done, I'm also done with countdown 1. So I take that off my call stack. So then where did we leave off before countdown 1? We left off with countdown 2. Well, what was left there? Well, we were on line 9 as well. And so there's nothing else to run for countdown 2. So we're done with countdown 2 as well. And the same process goes for countdown 3. And now we finish calling ourselves. And most importantly, when we look at our console log, we actually got the output that we wanted, which is print out all the numbers from num all the way down to 1, followed by done. Any questions? Right. Yeah. So when it goes down to the other plates, all it's really doing is picking up where it left off. Right. So like going back to the cake baking analogy, like if using the eggs was step 3 of 5, after you get the eggs, you keep going with step 4. You don't go all the way back to step 1, right? And so similar here is once we got countdown 0, we then took that off our call stack, and then we say, where do we leave off with countdown 1? Oh, we left off on line 9. So now that that's been resolved, well, there's nothing else, right? And so we just kind of work backwards from there. Okay, so the two main takeaways from the countdown function that we've seen, right? One is you need to define a base case. More succinctly, you need to know when to stop, right? Calling a function over and over again is actually not that hard. Knowing when to stop usually is a bit more trickier. And then secondly is, in order to get to that stopping point, your function must be changing the input each time it calls it, right? If we just call ourselves the same number over and over and over again, well, we would never stop. Even if we have a condition that says, if this condition is met, we will stop. The difficult thing is we would never meet that condition. So here, the recursive case must change the input so that every time we call it, the input changes in a way that gets us closer and closer to our stopping point. Recursion also becomes a lot more complicated when you have to return a value from the function. And so once again, we need to be very careful that we have a base case that tells us exactly when to return, and i.e. when to stop the function too. So let's take a look at an example of this. Let's think about something called a factorial. A factorial is a mathematical function that just takes a number and it gives you basically the product of all the numbers between 1 and that number. So if I do 5 factorial, that's just 5 times 4 times 3 times 2 times 1. If I do 4 factorial, it's just 4 times 3 times 2 times 1 and so on and so forth. If I wanted to write this function using recursion, what's a way for us to do it? Well, let's start with our, let me go back a few slides. Let's start with our base case, right? The base case here is lines 5 and 6, which is 0 factorial is equal to 1, and then 1 factorial is also equal to 1. So in that case, and if I get at the very, very basis of my factorial function, just saying, hey, I'll take it a num. If num is 0 or if num is 1, I just return 1, right? There's no more solving I need to do. It's just, it is what it is, okay? That's just all that's there. And so if I do factorial 0 or factorial 1, I get back 1 in both cases. Very clear cut, right? Now, how do we handle it if the number is bigger than 1? Well, if we look at our input again, remember, 5 factorial is 5 times 4 times 3 times 2 times 1. But 4 times 3 times 2 times 1 is actually just 4 factorial. And in fact, if we work our way down, one pattern that we'll see that for any number that's greater than 1, so 2, 3, 4, 5, the factorial of that number is equal to that number multiplied by the factorial of that number minus 1. So 4 factorial is just 4 times the factorial of 3. And 3 factorial is just 3 multiplied by the factorial of 2, and so on and so forth. And now using this pattern, it actually gives us a little bit of a way to start thinking about how do we solve this problem using recursion. Okay, because every value is just the number multiplied by the factorial of that number minus 1. Well, if I do factorial 2, for example, one way for us to do is actually just to write, okay, if num is 0 or 1, we can return 1. Otherwise, let's call factorial of num minus 1. So what's the factorial of this number minus 1? And now when we do factorial of 2, the first time we feed it in, num is 2, so it's not 0 or 1, so we skip the if clause. On line 9, we say, well, what's the factorial of 2 minus 1? It's 1. And what's the factorial of 1? It's 1. So we're getting close now. We're not quite at the answer just yet, right? Because remember, the factorial of any number greater than 1, it's that number multiplied by the factorial of that number minus 1. And so here, if I just do console log out the number num multiplied by the factorial of num minus 1, and I do factorial 2, I get back factorial 2 is equal to, on line 8, 2 multiply factorial of 2 minus 1, so factorial 1. Factorial 1, if I recursively call that function again, if num is equal to 1, it will hit line 3, it will say num is equal to 1, and on line 4 it will return 1. And then we're done with that function, right? Because once we hit a return, we're done with the function. So then we go back to where we left off. And therefore, if I actually, and therefore 2 times 1 is just 2. Okay. So now I've actually kind of extrapolated this idea that the factorial of a number, if it's 0 or 1, it's just 1. Otherwise, the result is going to be the number multiplied by the factorial of that number minus 1. And once I get that value, I'll return that value on line 9. So if I want to call factorial 2, I get back 2. If I want to call factorial 5, let's do our old call stack walkthrough again. And hopefully it's a little more clear. On factorial 5, I feed in num is 5, right? I go to lines 3 through 5. I skip that because num is not 0 or 1. On line 7, it says let result, aka whatever we're going to be returning, it's equal to 5 multiplied by factorial of 5 minus 1, which is 4. And everyone sees it on the bottom right-hand corner there. The call stack for factorial 5, we're currently leaving it off as 5 multiplied by factorial 4. Well, that means in order for us to finish resolving factorial 5, we need to figure out what factorial 4 is, and then multiply it by 5. So that means we're recursively calling ourselves now, and we need to figure out what factorial 4 is. Well, when we call factorial 4, where num is 4, we still skip lines 3 through 5, and we get to line 7 again, except now we're trying to return 4 multiplied by factorial of 4 minus 1, which is 3. So what's factorial 3? Factorial 3 is just 3 multiplied by factorial 2, and then what's 2? What's factorial 2? Factorial 2 is just 2 multiplied by factorial 1. Well, what's factorial 1? Factorial 1, if num is equal to 1, well, we go to line 3, num is equal to 1. On line 4, it just returns 1. Does everyone see that on the bottom right-hand corner there? Factorial 1, we got an answer. It's just 1, right? And that means now we can return the number 1 to whoever requested to know what factorial 1 is, which it was under factorial 2. So we just replace that value now with 1, and therefore factorial 2 becomes 2 multiplied by 1, which is just 2. Well, who wanted to know what factorial of 2 was? Well, factorial 3 did, because it wanted to know what 3 multiplied by factorial 2 was. So that boils down to 3 multiplied by 2, which becomes 6. And then we go down again. Factorial of 4, want to know what factorial 3 was, so I can multiply it by 4. So then we get 4 times 6, which is 24. And then last but not least, we go back to where we left off and we return 5 multiplied by factorial 4, which is 24, which gives you 120. And that becomes our final answer. Did that make sense, folks? Yes? Yeah, all the slides that we've gone over so far, this entire curriculum is available on the platform. Yeah. Any questions? Reed, Vitali, Hillary? You guys all good? Okay, great, cool. So look at our factorial functions. The approach that we took is very similar to what we did before, right? Write our base case first and test it with simple inputs, right? Testing with simple inputs is usually just faster and a little bit more clear cut than trying to test. Imagine we had to solve factorial of 100, right? That would be very messy very quickly. And then as our function does better against simpler inputs, we want to increase it to more and more complex inputs. I'll skip the debugger for now. Okay, so recursion can be used with any data type in JavaScript, although it's most commonly used for arrays or strings. If, for example, I want to find the sum of all the numbers in an array, a for loop, once again, works perfectly fine, right? A for loop is actually a great way for us to add up all the numbers in an array. But if I think about the way the recursion works, well, a recursion would just say, let's just keep processing the next item in the array until I reach the end of the array. It sounds kind of like a for loop, except the approach is different, right? With a for loop, in the very beginning, we're predefining array.length equals this, and we're going to stop when we hit there. With recursion, we're just saying, hey, let's just keep processing in the array until we reach the end, and I don't know when the end is. And so tomorrow, when we look at the recursion problems, one thing that we'll see recursion kind of be able to solve in a way that for loops can is how do we solve a problem in which we don't know how many times we need to do it beforehand, right? If we know how to do it, if we know we want to do it 6 times, just write a for loop that iterates 6 times. If I don't know how many times it's going to take, well, then it becomes a lot trickier. So cannot emphasize enough, please start with the base case, test it with the simple inputs, and then always test to make sure that you're returning the right thing and you want your function to end at the right place. Yeah, okay. So that was it for today, and I cannot reiterate enough. We can do the problems today. All the problems should only be one function. Don't try using a for loop if you can avoid it, because in most cases, if you use a for loop, you're kind of using an entirely different approach than recursion. And then last but not least, don't use big variables that exist outside of the function, right? If you have a global function, if you have a global variable somewhere, like let sum equals 0, and you have a function that just modifies that global variable sum, well, that's not really recursion, because then you're just using a for loop and just writing it differently, right? A recursive function should be self-contained, as in all of the variables that you need are going to be inside that variable, and any value you want to return is going to be contained inside that function. Okay, so if you find yourself writing multiple functions, it's a red flag, you're not doing something right. And then if you're modifying one variable outside of the recursive function, that also means you're doing something not right. So just kind of keep that in mind as you work on these problems. Are there any questions before we open up the workshops?